very important theorem that in non-empty subset H, a non-empty subset H of a group G is a subgroup of G if AB belongs to H. This implies AB belongs to H. A belongs to H, this implies A inverse belongs to H. So, first condition is if two elements of H, then their product also element of H, that means it satisfies the closure property, and also there exists inverse of each element. If A belongs to H, this means inverse also belongs to H. Now, shifting to the proof of this theorem. Let us take the first part, that H subgroup of G. We will satisfy the two conditions. When it is a subgroup of G, then it means it is a group of G. It is group. Every subgroup is a group. So, it means it satisfies all those four conditions. So, first condition here is closure property. So, it satisfies the first condition, and second condition is of inverse, and because it is a group, it satisfies the second condition also. So, both the conditions first and second are satisfied because H is a subgroup of G. Now, conversely, we are taking that both the conditions are satisfied, we will prove that H is a group. To prove H is a group, we will take all the four conditions. First condition was closure property. Closure holds in H because of first condition. For what is first condition? That if AB belongs to H, AB also belongs to H. So, that is given. So, because two conditions are satisfied, so it means closure property is satisfied. Then taking second property of associativity, take three elements of A, B, C belongs to H. Now, H is subset of G. So, it means when H is subset of E, each and every element of H is also the element of G. So, A, B, C belongs to G, but G is a group. So, if G is a group, this implies associativity is satisfied, hence associativity hold in H. So, second condition is satisfied. Also, for any A belongs to H, A inverse belongs to H because of second condition, because second condition states that if A belongs to H, A inverse belongs to H. Then A into A inverse, what is A into A inverse? That is E. A inverse belongs to H, this implies E belongs to H, this implies H has an identity. Then inverse of each element of H is in H by second condition. So, all the four conditions of closure, associativity and identity and inverse are satisfied. Hence, H satisfies all the conditions in the definition of a group, and thus it forms a group. Therefore, it is a subgroup of G. A subset is a subgroup of G if it is a group, as we defined earlier. Now, taking another theorem, a non-void subset H of a group G is a subgroup if G of G, if AB belongs to H, this implies AB inverse belongs to H. What is a non-void subset? It means it is non-empty. It is always we are taking non-empty, non-void subset of H. There are some elements always in H. So, it is a group if AB belongs to H, this implies AB inverse belongs to H. Now, shifting to the proof of this theorem. Now, H is a subgroup of G. We will say, we will take H is a subgroup of G. Then, if AB belongs to H, then this implies AB inverse belongs to H. How come? H is a subgroup of G, then it means it is a group, and if A belongs to H, B belongs to H, this implies B inverse also belongs to H. So, if A belongs to H, B inverse belongs to H, this implies AB inverse belongs to H because of closure property. When two elements belongs to H, then their product also is an element of H. So, that follows from the definition. Now, conversely, let the given condition is satisfied, that is if AB belongs to H, AB inverse also belongs to H. Now we will prove that H is a subgroup of G, that is we will prove that H is a group. Then H is a group, we will take all the 4 assumptions, 4 postulates. Now associability holds in H. How come associability holds in H? Because H is a subset of G and A belongs to H, then be any element of A, then A belongs to H, this implies A inverse belongs to H, this implies E belongs to H. So H has identity. Again for any A belongs to H, E belongs to H, A inverse belongs to H, A inverse belongs to H. So H has inverse element. So finally closure property, AB belongs to H, AB inverse belongs to H, this implies B inverse belongs to H, this implies AB belongs to H. That is H is closed under multiplication. So H forms a group as it satisfies the all those 4 conditions which makes a set to be a group. So H is subgroup of G. Now what is center of the group? If G is a group, let Zg is equal to x belongs to G such that xg is equal to gx for all G belongs to G. Then Zg is called the center of the group. That is, if we are taking any element of G and we are taking another element of G, then the commutative property holds, then we say that Zg is the center of the group. Taking up the theorem, center of a group G is a subgroup of a G. Z means Zg is always a subgroup of G. So we will prove that Zg is a group. Let Zg is the center of the group. So then Z is not equal to phi because there always exists any element, and as E belongs to Zg, again xy belongs to Zg. This implies by definition xg is equal to gx. This implies yg is equal to gy for all G belongs to this. This implies G inverse x inverse is equal to x inverse G inverse and G inverse y inverse is equal to y inverse G inverse. That is by definition of center of a group. Now Gxy inverse is equal to Gxy inverse, which is equal to Xgy inverse, which is equal to Xgy inverse into G inverse G. So we are just changing the combination. Now Xg we are taking out, Y inverse G inverse into G. So Xg is equal to G inverse Y inverse G. So which is equal to X G inverse Y inverse G. So which is equal to X Y inverse G for all G belongs to G. So X Y inverse belongs to G. So from we started from G X Y inverse and we reached on again on the commutative property X Y inverse G. So when this is satisfied, then Zg, so it means it belongs to G. So all the properties of a group are satisfied, hence Zg is a subgroup. Show that union of two subgroups may not be a subgroup. Let Ht is equal to 2n, n belongs to Z, and H3 is equal to 3n, n belongs to Z. Here Z is a set of integers. So we are taking a group of Z with operation plus. Now H2 and H3 will be subgroups of Z. Indeed, 2n minus 2m is equal to 2, n minus 1 belongs to H2. Now, H2 union H3 is not a subgroup, as 2 3 belongs to H2 union H3, but 2 minus 3 is equal to minus 1 does not belongs to H2 union H3. Then union of two subgroups is a subgroup if one of them is contained in other. Let H and K be two subgroups of G, and suppose H is subset of K, then H union K is K, which is a subgroup of G. Conversely, let HK be two subgroups of G. So, H union K is also a subgroup of G. We show one of them must be contained in another. Suppose it is not true that H is not subset of K, K is not subset of H. It means there is one element in H which does not belong to K and another element in K which does not belong to H. So, then XY also XY belongs to H union K. Also XY belongs to H union K. Since H union K is a subgroup, so XY belongs to H union K, this implies Y belongs to H and XY belongs to K. If XY belongs to H, then X belongs to H and X inverse XY belongs to H, this implies Y belongs to H, which is not true because one is not contained in H. So, our supposition is wrong. So, one of them must be contained in another. Let H is a subgroup of G and let A belongs to G. If any element be any element, then what is right coset? If then H is said to be right coset. Right coset of H in G. There is always a 1-1 onto mapping between any two right cosets of H in G. All that is a result which we will use in Lagrange's theorem. What Lagrange's theorem states? If G is a finite group and H is a subgroup of G, then order of H divides order of G. So, if order of G is n, then corresponding to each element G, we can define a right cosets in H in G. The number of distinct right cosets of H in G is less than or equal to n. Using the properties of equivalence classes, we know that G is equal to HA1 union HA2 up to union HAT, where T is the number of distinct right cosets of H in G. Then order of H, G is sum of order of all the elements, then reminding us that two right cosets are either equal to or have no element in common. So, this implies order of G is equal to order of H plus order of H plus order of H, which means order of G is equal to T into order of H. So, order of H divides order of H G, because substituting the value of T, order of G is equal to order of H multiplied by some T. So, converse of Lagrange's theorem does not hold. Then if H and K are finite subgroups of a group G, then order of HK is equal to order of HK, H into order of K over order of H intersection K. So, for proof, let D be any H intersection K and it is a subgroup of K. So, if we are taking HK is equal to D K H union K, then no 2 of HK1 HKT can be equal to equal as if HKI is equal to HKJ, then that means DKI is equal to DKJ, which is not true. So, hence order of HK is the sum of all these elements, and substituting the value we got the result. So, whenever you need to know more about these groups and subgroups, do consult these references, or you can contact me. It is a special course in theory of groups by Robinson, and moreover the abstract algebra by Khanna and Bhamra is very good for this topic. Do come to me anytime you need my help. Thank you so much.